Okay, so we can say, okay, if P then Q, this means that P implies Q. The converse is if Q then P. And this would mean that Q would imply P. Okay. Now, when it comes to just a normal statement, if P is true, then Q is true, and its converse, the converse does not have to be true, okay? It's just going from one argument to the next, okay? So, one of the main ways that we talk about the converse in terms of calculus, I know this is getting a little outside of the realm of Greek, but if we're talking about logical arguments, this makes sense in my mind for a way to talk about this. Okay? So, if a function is differentiable, and y'all might not be familiar with exactly what this word means, but another way to talk about a function being differentiable, what is a word that would be common that we would use for this? Let's say smooth. Okay. So if a function is differentiable, meaning smooth, then it is continuous. And what is another common word that I would use for continuous? Okay, this would mean connected. Okay, so if a curve is smooth, then it has to be connected. Okay, the converse is not true. Okay. So if we have a smooth differentiable function, then it has to be continuous. I'm not going to go into all the technical details of exactly why this is true. It has to do with the limit laws that we'll cover in calculus. Okay, this is actually what I'm going over today with my students. Is concepts of differentiability and continuity. It's one of the first things you go over in calculus 1. Okay. Now, what do I mean by the converse is not true? Okay. So, when I say the converse is not true, let's say if a function, let me turn that off, is continuous, well, let's phrase it this way. And we will talk a little bit about the concepts of necessary and sufficient conditions. But what is really meant by this statement, okay? So, can we think of some type of function that would be continuous but not differentiable, okay? One way to think about this is, okay, so for a function to be continuous, it just has to be connected, okay? For a function to be differentiable, it has to be connected and smooth, right? So, I think we've actually talked about fractals in the past, but if we took a function that looked like this, you can kind of think about the stock market. So a function like this it is continuous. Those lines are connected, okay? When you end up with something that is discontinuous, there are holes or giant leaps. No, you can put your finger on this line and you can trace it all the way around and it's just really, really jagged. It's not smooth, okay? And even if you zoomed in, let's say I decided I wanted to take an image from right here and I wanted to blow it up, what would I still end up with? Is these horrible jagged lines. Now, this thing right here is continuous. Okay. This type of function right here, a lot of times we also call this random walk, okay? A function like this, it is continuous, but it is not smooth, hence differentiability is a stronger condition than continuity. So this normally goes into what conditions are actually stronger, okay? So, if a function is differentiable, which is a stronger condition, it has to be continuous because continuity is a weaker condition of than differentiability, okay? And so we'll talk about necessary and sufficient conditions. So, what do I mean by necessary? Okay? Okay. So let's talk about what is meant by necessary and sufficient conditions. Okay. So, let's just start off with P is a necessary condition. Of Q. Okay, so I used that word necessarily in the previous problem, okay? So in mathematics, we spend a lot of time talking about necessary and sufficient conditions, and they have kind of this strange language in a little bit, but in reality, the concept of necessary and sufficient conditions means which condition is really stronger, okay? So, for P to be a necessary condition of Q, okay? Meaning that if P is not true, let's isolate this a little bit. So, okay, so P is not true. Okay. All right, so now let's say, what do I meant by, in the previous problem, of having a necessary condition? So if P is true, then Q is not true, okay? So if I said, if a function is not differentiable, it is not continuous. Okay, now this directly contradicts what I just said. This is a false statement. Okay, so what do I mean by this being a false statement when it comes to necessary and sufficient conditions? Okay. I'm going to isolate that right there. So, isolate this just a little bit. Differentiability is not a necessary condition for continuity. Because this statement is false. Okay? So what's meant by that is that you can have a continuous function, but it is not necessary for that continuous function to be smooth. Okay? So that's what I mean by something that's necessary. So saying that a statement is necessary for another statement to be true means, yeah, if that statement's not true, then the other statement is not true. This is a false equivalence in this case, because you can have something being continuous but not being differentiable. Okay? They can be connected. That does not mean that they are smooth. Okay? Now, what is meant for the other term, which is sufficient? Okay? If a condition is sufficient, then it means the other condition is true. Okay? So differentiability is a sufficient condition for continuity. So if a function is smooth, then it has to be connected. Differentiability is a stronger condition. Okay? But differentiability, that smoothness, is not a necessary condition for it being continuous, okay, just meaning connected. So, if you ask what a sufficient condition is, okay, so let's say P is a sufficient